In the darkness between stars, something ancient just woke up. A visitor from another solar system older than Earth itself has begun to glow, to hum with invisible energy, to accelerate through space in ways gravity alone cannot explain. Take a slow breath. Let your thoughts settle like dust in starlight. Understanding what's happening to this interstellar wanderer could rewrite our assumptions about how comets behave, how magnetic fields emerge in the cold void, and whether the space between worlds is as empty as we think. On October 29, 2025, as 3I Atlas passed closest to our sun instruments, detected something extraordinary. A magnetic cocoon forming around it, bright plasma emissions, unlike anything seen from previous interstellar visitors, an acceleration that defies simple orbital mechanics. But how does a frozen relic from another star system suddenly come alive? And why is it moving faster now than when it arrived? Tonight, we drift together through the story of this celestial awakening. We'll explore what scientists observed as this visitor passed through the inner solar system, understand the elegant physics of magnetic fields born from sunlight and ice, and contemplate what it means when matter from distant stars touches the breath of our own sun. We'll examine the evidence, carefully separate fact from speculation, and consider what mysteries still linger in the data. This isn't just about one comet, it's about connection. The invisible threads that link every object in space, from the smallest grain of cosmic dust to the largest spiral galaxy. It's about how energy moves, transforms, and tells stories across distances we can barely comprehend. So close your eyes if you wish. Let the journey begin. The universe has sent us a messenger wrapped in ice and magnetism, and it's time we listened to what it has to say. Before we can understand what makes 3I Atlas extraordinary, we must first understand what it is. And that story begins on a summer night in the southern hemisphere when automated telescopes scanning the sky caught something moving. July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System. ATLAS for short operates a network of telescopes designed to find objects that might threaten Earth. In Rio Hurtado, Chile, one of these robotic sentinels captured images of a faint smudge of light moving against the background stars. The motion was unusual, too fast, too purposeful. Within hours, astronomers around the world turned their instruments toward this enigma. Take a slow breath and imagine that moment of recognition. Among millions of stars, one point of light behaving differently, one traveler that didn't belong. The mathematics were immediate and unambiguous. This object followed a hyperbolic trajectory, a path that doesn't loop back. Its orbital eccentricity measured 6.137, meaning its orbit is stretched impossibly thin, almost a straight line through space. For comparison, Earth's orbit is nearly circular with an eccentricity of 0.0017. This visitor wasn't gravitationally bound to our sun. It was passing through. The designation came swiftly, 3I Atlas. The 3I marks it as the third confirmed interstellar object to enter our solar system in recorded history. The first was 1I de Oumuamua in 2017, that strange tumbling visitor that sparked 1,000 questions with its elongated shape and unexpected acceleration. The second was 2I Borisov in 2019, a more conventional comet that behaved much as we expected. Now came the third. But archive searches revealed something remarkable. This object had been photographed before just not recognized. The Zwicky Transient Facility in California had captured it as early as May 21, 2025. For 6 weeks, 3I Atlas had drifted through our astronomical databases, hiding in plain sight against the dense star fields of the galactic center. Amateur astronomer Sam Dean noted it had likely gone unnoticed because it was crossing in front of the Milky Way's bright core, like trying to spot a moth against a streetlight. By July 2nd, observations from multiple sites confirmed what initial readings suggested: this was no asteroid. The Lowell Discovery Telescope in Arizona the Canada-France-Hawaii telescope on Mauna Kea, and Chile's Deep Random Survey all detected a faint coma, a cloud of gas and dust surrounding a solid nucleus. David Jewett and Jane Liu, astronomers who had helped discover the Kuiper Belt decades earlier, used the Nordic Optical Telescope to confirm that 3I Atlas was clearly active. It was a comet shedding material as it approached the sun. Take another breath and let these facts settle. An active comet from interstellar space, the third we've ever seen. The Hubble Space Telescope captured its portrait on July 21st, revealing a teardrop-shaped cocoon of dust surrounding the nucleus. The image showed something elegant light from distant stars streaked across the frame because Hubble was tracking the comet's motion, but the comet itself appeared sharp, wrapped in its luminous veil. Analysis suggested the nucleus, the solid icy body at the heart, was somewhere between 440 meters and 5.6 kilometers across. The uncertainty reflects the challenge of distinguishing the nucleus from its surrounding cloud. The James Webb Space Telescope, humanity's newest eye on the cosmos, observed 3I Atlas in early August with its near-infrared spectrograph. This wasn't merely taking a picture, it was capturing the object's chemical signature, reading the wavelengths of light absorbed and emitted by different molecules. The results told a story of frozen chemistry awakening carbon dioxide, water, vapor, carbon monoxide, carbonyl sulfide, and water ice, all streaming off the nucleus as sunlight warmed surfaces that had been cold for millions of years. NASA's SphereX mission caught it between August 7 and 15. ESA's Mars Express and ExoMars Trace Gas Orbiter attempted observations on October 3 as the comet passed within 28 million kilometers of the red planet, close enough that Mars orbiting spacecraft could study it, though it appeared only as a fuzzy white dot against the black 10,000 times fainter than their usual target. The trajectory itself told a deeper story. 3I Atlas was traveling retrograde backwards relative to the planet's orbital direction with an orbital inclination of just 5 degrees from the ecliptic plane. The ecliptic is the flat disk where the planets orbit, and most solar system objects follow it because they formed from the same spinning disk of gas and dust billions of years ago. But 3I Atlas came from outside that system. The fact that it aligned so closely with the ecliptic plane was statistically unusual. Random approaches from interstellar space should come from any direction. This alignment was noted, but not yet understood. The comet reached perihelion, its closest approach to the Sun, on October 29, 2025, at 11:27 Universal Time. At that moment, it was 1.36 astronomical units from the Sun, placing it between the orbits of Earth and Mars, about 203 million kilometers from our star. At that distance, it experienced solar heating of roughly 770 watts per square meter, enough to sublimate frozen gases and drive the outgassing that creates a comet's coma and tail. But here's what makes this moment particularly intriguing. Perihelion occurred just 8 days after solar conjunction, when the comet passed directly behind the Sun from Earth's perspective. For crucial weeks in October, we couldn't observe it. The bright glare of the Sun blocked our view precisely when the comet was most active. Only space-based solar observatories like GOES 19, SOHO, and Stereo could glimpse it during this period, and their observations revealed unexpected brilliance. Take a slow breath and consider the choreography. A visitor from another star approaching our Sun at the moment when Earth-based telescopes couldn't watch. Timing that raised eyebrows among some observers, though most attributed it to coincidence rather than design. The comet will make its closest approach to Earth on December 19, 2025, passing at a comfortable distance of 1.8 astronomical units, about 270 million kilometers. It poses absolutely no threat. From there, it will continue outward, passing Jupiter at 54 million kilometers on March 16, 2026, before leaving the solar system entirely headed back into the darkness between stars. Preliminary analysis suggests this traveler might be between 3 and 11 billion years old. potentially older than our entire solar system. For uncounted millennia, it drifted through the void, its volatiles kept frozen by the absolute cold of interstellar space. Now for this brief cosmic moment, it has entered the sphere of influence of another star, our star. And in that encounter, something remarkable began to happen. To understand what happened to 3I Atlas, we must first understand the invisible ocean in which all planets, comets, and spacecraft swim. We call it the solar wind, but it's unlike any wind on Earth. Imagine standing on the surface of the sun. Impossible, of course. But bear with the thought. The sun's corona, its outer atmosphere, is extraordinarily hot, over 1,000,000 degrees Celsius. At such temperatures, atoms don't remain intact. Electrons tear free from their parent nuclei, creating a sea of charged particles. Protons, electrons, and ionized atoms. This isn't ordinary gas anymore. It's plasma, sometimes called the fourth state of matter, neither solid, liquid, nor gas, but a fluid of free charges responding to electromagnetic forces. This plasma cannot be contained by the sun's gravity alone. At such high speeds, some particles reaching 400 to 800 kilometers per second, they escape into space, streaming outward in all directions. This exodus creates what we call the solar wind, a continuous flow of charged particles filling the entire solar system. Take a breath and picture this invisible tide. Right now, as you sit reading, solar wind particles are washing over Earth at hundreds of kilometers per second. We don't feel them because Earth's magnetic field deflects them, creating a protective bubble called the magnetosphere. The magnetosphere is one of nature's most elegant shields. Generated by the churning motion of molten iron in Earth's outer core, our planet's magnetic field extends tens of thousands of kilometers into space. When solar wind particles encounter this field, they cannot easily cross it. The charged particles spiral along magnetic field lines, most deflecting around Earth like water around a stone. But some particles slip through near the poles, where field lines dive down toward the surface. When these particles collide with oxygen and nitrogen in the upper atmosphere, they excite those atoms, which then release energy as light. We call this the aurora, the northern and southern lights. The aurora is the solar wind made visible plasma, transformed into luminous curtains of green, violet, and red. Every auroral display is evidence that we live within the sun's extended atmosphere. Other worlds show us variations on this theme. Jupiter, with its enormous magnetic field, creates auroras so powerful they produce more energy than all human civilization generates. These auroras pulse in rhythm with Jupiter's 10-hour rotation, painting the poles, with radiation strong enough to damage spacecraft. Saturn's auroras respond to its interaction with solar wind and to its massive moon Enceladus, which spews water vapor that becomes ionized and joins Saturn's magnetosphere. Even Mars, which lost its global magnetic field billions of years ago, shows ghostly auroras when solar wind particles strike patches of magnetized crust, fossil remnants of a magnetic field that once protected a thicker atmosphere. But comets are different. They have no internal magnetic field generated by rotating metal cores. Yet when they approach the sun, something remarkable happens. They create their own temporary magnetospheres through a process called magnetic field draping, or induction. Here's how it works. As a comet warms frozen volatiles, water ice, carbon dioxide, methane, ammonia sublimate directly from solid to gas. This outgassing creates a cloud called the coma, which can extend for thousands or even millions of kilometers. Ultraviolet radiation from the sun then ionizes some of these gases, stripping electrons away and creating charged particles, a plasma. When solar wind encounters this plasma cloud, it cannot easily flow through it. The wind's magnetic field lines drape around the obstacle, creating a boundary. If the outgassing is strong enough, this boundary becomes a miniature magnetosphere, an induced magnetic field shaped not by internal dynamics, but by the interaction between solar wind and the comet's own atmosphere. This isn't a permanent structure. It exists only as long as the comet remains active and the solar wind continues to blow. But while it lasts, it's real. Instruments can measure its strength, map its shape, and observe how it deflects incoming particles. The Rosetta mission gave us our first close-up look at this process. From 2014 to 2016, the European Space Agency's spacecraft orbited Comet 67H Churyumov-Gerasimenko, watching as it approached the Sun and became active. Rosetta's magnetometer detected the formation of an induced magnetosphere, observing how solar wind particles were deflected and how the comet's plasma environment changed day by day. What Rosetta found was extraordinary. The induced field wasn't static, but dynamic, breathing in rhythm with solar activity. When the Sun released bursts of radiation, solar flares or coronal mass ejections, the comet responded within hours. Its outgassing increased the coma, brightened, and the magnetic boundary shifted and strengthened. Take a slow breath and imagine this delicate dance. The Sun exhales radiation. The comet responds by releasing gas. The gas becomes plasma. The plasma shapes the magnetic field. The field protects the nucleus from the harshest radiation. It's a feedback system, an elegant conversation between star and wanderer conducted in the language of electromagnetic force. Another crucial effect shapes cometary behavior: radiation pressure. Photons, particles of light, carry momentum. When sunlight strikes dust grains and gas molecules flowing off a comet, it pushes them. This pressure is minuscule for any individual photon, but the Sun emits an astonishing number of photons. The cumulative effect pushes gas and fine dust away from the Sun, creating what we see as the comet's tail. In fact, comets typically have two tails. The dust tail, made of heavier particles, follows a curved path as the comet orbits. But the ion tail, made of charged gas molecules, responds to the magnetic field embedded in the solar wind. This tail points almost directly away from the Sun, sometimes extending for millions of kilometers, glowing blue from ionized carbon monoxide. These are the physical principles at play when any comet approaches the Sun: sublimation, ionization, plasma formation, magnetic field induction, and radiation pressure. Scientists have observed these phenomena in dozens of comets. The physics is well established, confirmed by missions like Rosetta, by ground-based observations, and by theoretical models that match what we see. What makes 3I Atlas intriguing is not that these processes occurred, that's expected, but rather the strength, timing, and characteristics of what observers detected. Something about this interstellar visitor's interaction with our Sun's breath was unusual enough to make scientists take special notice. And that's where our story truly begins. As 3I Atlas drew closer to the Sun through the summer and fall of 2025, astronomers watching from Earth and space began to notice changes. The comet was waking up, shedding the frozen sleep of interstellar transit. The brightening was gradual at first. Through July and August, the comet's apparent magnitude, its brightness as seen from Earth, hovered around 13 to 14, far too faint for binoculars or amateur telescopes, requiring substantial instruments even to detect. But it was brightening steadily as solar radiation increased, warming the nucleus and driving more vigorous outgassing. Spectroscopic observations during this period revealed the comet's chemistry. Multiple observatories, including the Very Large Telescope in Chile and the SOAR telescope, analyzed the light coming from 3I Atlas's coma. What they found was both expected and surprising. The expected part: water vapor, carbon dioxide, and carbon monoxide, standard ingredients of cometary composition. Comets are often described as dirty snowballs, mixtures of ice and dust left over from the formation of planetary systems. Water ice is ubiquitous. Carbon dioxide sublimates easily even at large distances from the Sun. Carbon monoxide is a volatile that scientists use as a tracer of a comet's activity. The surprise and unusually high abundance of nickel vapor in the coma. Nickel is a metal not normally prominent in cometary emissions. Its presence suggests a composition richer in metallic elements than typical solar system comets. This finding was published in late October by researchers including Darrell Seligman, a physicist at Michigan State University, who has been studying interstellar objects. The nickel signature grew stronger as the comet approached perihelion, indicating that deeper metal-enriched layers of the nucleus were being exposed as outer layers sublimated away. This metallic richness might tell us something profound. The stellar nursery where 3I Atlas formed the molecular cloud around some unknown star billions of years ago might have had a different chemical composition than the cloud that birthed our solar system. Every star, every planet, every comet is made from the debris of previous generations of stars. When massive stars explode as supernovae, they scatter heavy elements through space. The mix varies, depending on the history of stellar evolution in each region. 3I Atlas's unusual composition is like a passport stamp evidence of distant origins. Take a breath and consider that. This object carries within it the chemical signature of another star system, perhaps from the other side of the galaxy, perhaps from a stellar nursery long since dispersed. As perihelion approached, the comet's behavior became more dynamic. Observers noted fluctuations in brightness that seemed to correlate with solar activity. When the sun released flares, explosive releases of magnetic energy from its surface, 3I Atlas appeared to respond within hours. This suggested a coupling between solar radiation and cometary outgassing, exactly what we'd expect from a comet whose activity is driven by solar heating. But then came the crucial period, October 21st to November 8th, when 3I Atlas passed through solar conjunction and perihelion. For these critical weeks, Earth-based telescopes couldn't observe the comet directly. It was lost in the glare of the sun. Only specialized solar observatories could catch glimpses. The GOES 19 weather satellite designed to monitor the sun for space weather, forecasting captured images of 3I Atlas during this period. What it saw surprised mission scientists. The comet had brightened dramatically, reaching magnitude 12 or brighter, several times more luminous than expected. Similar observations came from SOHO, the Solar and Heliospheric Observatory, and from the twin stereo spacecraft that orbit the Sun at different positions than Earth. These spacecraft saw unprecedented brightening and noted something unusual. The color appeared bluer than expected, suggesting changes in the plasma environment around the nucleus. When 3I Atlas emerged from behind the Sun in early November, astronomers were ready. The Lowell Discovery Telescope captured images on October 31st, showing a bright coma and a faint tail. The Nordic Optical Telescope's observations, led by David Jewett and Jane Liu, tracked the evolution of the tail structure. What had been an aus-ante-tail in July and August, a sunward jet of material likely an optical illusion from perspective, had transformed by September into a more conventional tail pointing away from the sun. Most intriguingly, measurements of the comet's position over time revealed something that shouldn't happen. If the comet were following a purely gravitational trajectory, it was accelerating. Specifically, it was experiencing non-gravitational acceleration, a change in velocity, not explained by the sun's gravity or the gravitational pull of planets. This sounds mysterious, but it's actually common in comets. The mechanism is straightforward. When a comet's nucleus rotates and outgasses, jets of vapor act like tiny rocket engines. If the jets are asymmetric, more gas released from one side or during certain parts of the rotation, they create a net thrust. Over time, this rocket effect can noticeably change a comet's orbit. What made 3I Atlas's acceleration interesting was its magnitude and timing. The effect appeared stronger than what the visible outgassing alone seemed to account for. Some scientists suggested this might indicate carbon monoxide, which sublimates at lower temperatures than water ice, was driving activity from deeper in the nucleus, creating thrust we couldn't directly observe because the jets were emerging from the night side of the tumbling nucleus. Another fascinating observation came from an unexpected source. NASA's Europa Clipper spacecraft, launched to study Jupiter's icy moon, was cruising through the inner solar system during its gravitational assist trajectory. Between October 30th and November 6th, scientists calculated that Europa Clipper might pass through 3I Atlas's ion tail, the stream of charged particles extending behind the comet. This would be the first time a spacecraft encountered the ion tail of an interstellar comet. The Clipper's instruments weren't specifically designed for comet science, but they include magnetometers and particle detectors that could in principle detect changes in the solar wind caused by cometary material. If the encounter occurred, and if instrument teams decided to take data, it might reveal details about the density composition and magnetic structure of the tail. The data, if collected, wouldn't be available immediately due to Europa Clipper's communication bandwidth limitations, but it represented a serendipitous scientific opportunity. By late November, as 3I Atlas moved away from the Sun and became easier to observe from Earth, astronomers could see that it remained active, still producing a coma, still shedding material. The mass loss rate estimated from the brightness and extent of the coma suggested the comet was losing approximately 2 million tons of material during its perihelion passage. This sounds enormous until you realize it represents only about 0.05% of the comet's total estimated mass. Take a slow breath and let that sink in. The nucleus is shedding what amounts to a thin skin, perhaps just 4 centimeters of depth on average, revealing but not exhausting its ancient stores of ice. The comet continues outward, now moving at roughly 68 kilometers per second relative to the Sun. It will pass near Venus in early November at a distance of about 97 million kilometers, close in astronomical terms, though far too distant for Venus's gravity to significantly affect its path. The close approach to Earth happens December 19th, and then onward to Jupiter in March 2026. Throughout this journey, telescopes will continue to watch, spectrographs will continue to analyze its chemistry, and scientists will continue to refine their understanding of what this visitor from beyond has revealed about the physics of comets, the nature of plasma, and the invisible architecture of magnetic fields in space. But one question lingers in the observations, a subtle thread that some researchers find compelling. Why did this comet arriving from interstellar space align so closely with the ecliptic plane? Why did it reach perihelion precisely when Earth couldn't observe it? And why does its acceleration seem slightly larger than simple outgassing models predict? These questions don't have definitive answers yet, but they invite us to explore the hypotheses, the natural explanations, the unusual possibilities, and yes, even the speculative scenarios that push the boundaries of what we consider likely. Let's examine them one by one with the care and rigor that science demands. Before we venture into what makes 3I Atlas unusual, let's understand the exquisite physics of how magnetic fields emerge around comets. This is science at its most elegant, simple principles, combining to create complex beauty. Imagine you're floating beside 3I Atlas in early October as it draws near the Sun. The nucleus below you is dark and irregular, perhaps 5 kilometers across, about the size of Manhattan Island, pocked with craters and ancient scars. Its surface is not pure white ice, but dirty, almost black, coated with dust and organic compounds formed from radiation processing over billions of years. As sunlight strikes this surface, transformation begins. The ice doesn't melt, there's no atmosphere to maintain liquid water. Instead, it sublimates, turning directly from solid to vapor. Water molecules, Carbon dioxide molecules, carbon monoxide all suddenly become gas, escaping the weak gravity of the nucleus at several hundred meters per second. This isn't uniform. Jets erupt from specific locations where ice lies close to the surface or where cracks allow gas to escape. Some jets are strong visible in telescopic images as bright plumes. Others are faint, detectable only through careful measurement. As the nucleus rotates, probably tumbling chaotically rather than spinning smoothly, these jets turn on and off, creating a complex fluctuating flow of material into space. The escaping gas expands rapidly in the vacuum, forming the coma, the tenuous atmosphere surrounding the nucleus. Near the surface, this atmosphere might be relatively dense, but it thins quickly. A few hundred kilometers from the nucleus, the density is already similar to the best vacuum we can create on Earth. A few thousand kilometers out, it's comparable to interplanetary space itself. But here's where the magic begins. Ultraviolet radiation from the sun, the same wavelengths that cause sunburn on Earth, strikes these gas molecules. The photons carry enough energy to knock electrons free from atoms, ionizing them. A water molecule becomes a positive ion and a free electron. Carbon monoxide becomes CO+. Carbon dioxide breaks into fragments. These ions and electrons don't simply drift away. They carry electric charge, and charged particles respond to magnetic fields. The solar wind streaming past the comet at hundreds of kilometers per second carries the sun's magnetic field with it frozen into the plasma like a current frozen in amber. When this magnetically laden wind encounters the comet's ionized coma, it cannot easily penetrate. Think of it like a stream flowing around a boulder. The water can't pass through the stone, so it diverts around it, creating eddies and a wake downstream. Similarly, the solar wind can't pass through the dense plasma of the coma. It diverts around it, and in doing so, it drapes its magnetic field around the obstacle. This draped field creates a boundary called the com-topause, the interface between the solar wind and the cometary plasma. Outside this boundary, the solar wind dominates. Inside, the comet's own plasma dominates. The boundary itself is a region of intense activity. Magnetic fields, compressed particles accelerate, and electromagnetic waves propagate through the plasma. If the comet's outgassing is strong enough, this boundary can become substantial, large enough to significantly deflect the solar wind, creating a structure that acts like a miniature magnetosphere. It's not a magnetic field in the usual sense. The comet doesn't have a magnetic dynamo like Earth, but the effect is similar. The induced magnetosphere shields the nucleus from the direct impact of the solar wind. This was exactly what the Rosetta mission observed at Comet 67P. The spacecraft's magnetometer detected the formation of this induced field as the comet approached the sun. The field's strength grew as outgassing increased. When solar flares sent bursts of enhanced solar wind toward the comet, the induced magnetosphere compressed and strengthened, then relaxed when the burst passed. The boundary wasn't smooth and stable. It rippled and pulsed, responding to changes in both the solar wind and the comet's outgassing rate. Waves called Alphen waves and magnetosonic waves propagated through the plasma, transferring energy from one region to another. These waves are the plasma equivalent of sound waves, compressions and rarefactions that travel through the charged gas. Take a breath and imagine this invisible architecture. Around the dark nucleus, a luminous shell of plasma threaded with magnetic field lines that curve and twist. Solar wind particles approaching this barrier, most deflected, some spiraling along field lines, a few penetrating deep into the coma. And within this dynamic, ever-changing environment chemistry, occurring molecules breaking apart, recombining, emitting light at specific wavelengths that astronomers can analyze to determine what elements are present. Another force plays a crucial role: radiation pressure. Each photon from the sun carries a tiny amount of momentum, When photons strike dust grains in the coma, particles ranging from nanometers to millimeters in size, they transfer that momentum, pushing the grains away from the sun. The effect is small for any single photon, but the sun emits approximately 10.45 photons per second. The cumulative push is significant. For gas molecules and ions, the situation is more complex. They can absorb photons at specific wavelengths, gaining momentum. But ions also respond to the magnetic field carried by the solar wind. The result is that neutral gas and dust form one tail, curving slightly along the comet's orbit, while ionized gas forms a separate tail that points almost directly away from the sun, shaped by magnetic field lines. This ion tail can extend for enormous distances, tens of millions of kilometers in extreme cases. It's visible to the naked eye when bright comets pass near Earth, appearing as a bluish stream distinct from the yellowish dust tail. The blue color comes primarily from ionized carbon monoxide, which emits light at a characteristic wavelength. Here's something wonderful: we can calculate the force balance in this system. On one hand, we have the outward pressure, radiation pressure, thermal pressure from heated gas, and electromagnetic forces from the interaction with the solar wind. On the other hand, we have the inward pull, the weak gravity of the nucleus, and the confining pressure of the solar wind. Where these forces balance, we find the boundaries, the collisionopause, where the comet's neutral gas collides with the solar wind, the ionopause, where ions dominate the magnetic pileup boundary, where the solar wind's magnetic field accumulates. These aren't sharp boundaries, but transition regions, layers of different conditions. Scientists can model this entire system using magnetohydrodynamics, the physics of how plasmas move and interact with magnetic fields. The equations are complex, but the underlying principles are straightforward. Conservation of mass, conservation of momentum, conservation of energy, and Maxwell's equations of electromagnetism. When researchers run these simulations and compare them to observations like those from Rosetta, they find remarkable agreement. The models predict where boundaries will form, how strong the magnetic field will be, how plasma will flow, and observations confirm these predictions. This is the standard picture of comet-solar wind interaction. It's been refined over decades of observations and theory. It's taught in graduate courses in planetary science. It explains what we see in dozens of comets observed from Earth and visited by spacecraft. And it almost certainly explains most of what happened with 3I Atlas. Almost. Because in the details, in the timing, in the strength of certain effects, in the specific pattern of acceleration, some scientists notice features that made them pause, features that invited closer examination and perhaps alternative interpretations. But before we explore those alternatives, let's establish the baseline clearly, the natural conventional explanation that most astronomers consider most likely. Now we arrive at the heart of the matter, what makes 3I Atlas intriguing enough to warrant special attention. Let's inventory the unusual characteristics separating observation from interpretation. First, the trajectory. An orbital eccentricity of 6.137 makes this one of the most hyperbolic objects ever observed entering the solar system. Compare this to 1I Oumuamua, which had an eccentricity of approximately 1.2 and 2I Borisov at about 3.4. 3I Atlas is following an even, straighter path barely curved by the sun's gravity. This suggests an extremely high velocity relative to the sun, approximately 68 kilometers per second at perihelion, and an origin far from any gravitational influence. The mathematics of orbital mechanics tells us something interesting about such highly eccentric orbits. They're most likely to come from directions distributed randomly across the sky. The galaxy has no preferred orientation relative to our solar system's ecliptic plane. Yet 3I Atlas arrived almost perfectly aligned with that plane, inclined only 5 degrees. What are the odds? Roughly 5% of randomly arriving interstellar objects should fall within 5 degrees of the ecliptic. Not impossible 1 in 20, but notable enough to warrant comment. Some researchers, including Harvard astrophysicist Avi Loeb, have pointed out that this alignment would be more likely if the trajectory had been influenced by something other than pure ballistic motion through the galaxy. Second, the timing. Solar conjunction. When the comet passes directly behind the Sun from Earth's perspective, occurred on October 21, 2025, perihelion. The closest approach to the Sun occurred October 29, just 8 days later. This meant that during the period of maximum solar heating and activity when outgassing should be strongest, and the comet's behavior most interesting Earth-based telescopes couldn't observe it. This is coincidence. Orbital mechanics has no awareness of Earth's viewing geometry, yet it's an unfortunate coincidence from a scientific standpoint. The data gap during this critical period means we're missing direct observations of how the comet behaved at its most active. Third, the mass. Based on estimates of the nucleus size, likely 3 to 5 kilometers in diameter, and assuming typical cometary density around 500 kilograms per cubic meter, roughly half the density of water. 3I Atlas has a mass perhaps 1,000 times greater than 2I Borisov and 1,000,000 times greater than 1A Oumuamua. This makes it by far the most massive confirmed interstellar visitor. Why does mass matter? Because the probability of an interstellar object entering the solar system depends on how many such objects exist in the galaxy. Smaller objects are more numerous than larger ones. This is universal across all size ranges we observe from asteroids to planets. A 5-kilometer interstellar comet should be far rarer than a 100-meter one. The fact that only the third interstellar object detected happens to be so large is statistically surprising, though not impossible. Fourth, the acceleration. Analysis of the comet's position over time revealed non-gravitational acceleration changes in velocity beyond what solar and planetary gravity predict. This is common in comets. Outgassing naturally produces thrust. What caught attention was the magnitude of the acceleration compared to the observed brightness of the coma. Typically, scientists can estimate outgassing rates from how bright the coma appears. More gas means more light scattered by dust, and more emission from ionized molecules. They can then calculate how much thrust that outgassing should produce. For 3I Atlas, the acceleration appeared slightly larger than this simple calculation predicted. One explanation: carbon monoxide. This molecule sublimates at much lower temperatures than water ice and produces minimal dust. Strong CO jets would produce thrust without proportionally brightening the coma. If 3I Atlas's nucleus is rich in CO, possible if it formed in an especially cold region of its birth nebula, then hidden jets could explain the acceleration. Another factor: rotation. If the nucleus spins and if jets are asymmetrically distributed, as they always are in real comets, the spin cycles the jets in and out of sunlight, creating a pulsed thrust. Depending on the rotation period and jet distribution, this can produce net acceleration in various directions. Without detailed observations of the nucleus's rotation impossible at the vast distances involved, we can't precisely predict the thrust pattern. Fifth, the composition. The detection of nickel vapor is unusual. Most solar system comets show primarily rock-forming elements, silicon, magnesium, iron in their dust and water ice-dominated volatiles. Nickel presence isn't unheard of. It's detected in some comets, but its prominence in 3I Atlas's spectrum was higher than typical. This likely reflects the chemical composition of the molecular cloud where the comet formed. Different regions of the galaxy have different metallicities, the abundance of elements heavier than hydrogen and helium depending on the local history of stellar evolution. A cloud enriched in supernova ejecta might produce icy bodies richer in metals. Sixth, the behavior during perihelion. The limited observations from solar spacecraft showed unexpectedly bright emissions and a bluish coloration suggesting specific plasma processes. The details remain preliminary. Solar observatories aren't optimized for cometary science, but they hint at a vigorous, induced magnetosphere and strong ionization. Take a breath and step back. What do we have? A large metal-rich comet from interstellar space, arriving nearly aligned with the ecliptic, experiencing strong acceleration observed imperfectly, due to viewing geometry showing vigorous plasma activity. Each individual characteristic has a plausible natural explanation. Together, they form a pattern that invites multiple interpretations. This is where the scientific process becomes interesting. How do we weigh evidence, construct hypotheses, and determine which explanation is most likely? Let's examine them systematically, starting with the most probable. The first and most scientifically supported hypothesis is straightforward. 3I Atlas is an ordinary interstellar comet behaving according to well-established physics. Everything we observe can be explained by natural processes without invoking anything unusual. Let's build this case carefully. Start with the composition. The detection of elevated nickel suggests formation in a molecular cloud with higher metallicity than the one that birthed our solar system. This isn't exotic, it's expected. Our galaxy contains clouds with a range of metallicities. Some regions have been enriched by many generations of supernovae, others less so. Metallicity affects what kinds of planets and comets form. An iron-rich planetesimal belt might produce comets with higher metal content. The nickel also offers a mundane explanation for something else, the object's dark surface. Metallic grains mixed with organic compounds could create a surface with low reflectivity, and albedo perhaps as low as 0.03 or 0.004, making the object appear dark and difficult to detect until it came close. This matches observations of other comets, which often have surfaces darker than coal. Now consider the outgassing. As 3I approached, the sun, increasing solar radiation, warmed the nucleus. Water ice remains largely frozen beyond about 3 AU, 3 times Earth's distance from the sun, but carbon dioxide begins to sublimate at 5 to 7 AU, and carbon monoxide can be active even farther out. This creates a sequence of events. At large distances beyond 5 AU, CO sublimates from the nucleus, creating faint outgassing. This material carries dust, forming a thin coma, invisible to all but the largest telescopes. The comet appears inactive. At intermediate distances, 3 to 5 AU, CO2 joins CO in sublimating. Outgassing strengthens. The coma becomes detectable. This is when Atlas discovered the object in July 2025 at approximately 4 AU from the Sun. At closer distances, 1-3 AU water ice begins to sublimate from the surface and near-surface layers. This is the major volatile. Most comets are predominantly water ice. Outgassing becomes vigorous. The coma and tail become prominent. At perihelion, 1.36 AU maximum heating, water sublimates vigorously. The inner coma becomes a bright, dense cloud of gas and dust. Jets erupt from the nucleus. An induced magnetosphere forms from the interaction between this plasma and the solar wind. This sequence is textbook cometary behavior. The James Webb observations confirmed it. They detected CO2, H2O, CO, and other species in exactly the proportions consistent with a comet warming from the outside in. The acceleration standard rocket effect. Imagine the nucleus as a lumpy, rotating iceberg releasing jets of vapor. If a jet points in one direction as the nucleus rotates, it produces thrust in the opposite direction, Newton's third law. If jets are distributed asymmetrically, as they always are, and if the rotation isn't perfectly regular, likely given the nucleus's irregular shape, the time average thrust can be in almost any direction. Detailed calculations show that outgassing rates sufficient to produce the observed coma, brightness can also produce the observed acceleration, especially if CO, which is difficult to observe directly, dominates the gas production. CO produces less visible emission than water vapor, or CO2, so it can generate significant thrust without proportionally brightening the coma. The trajectory alignment with the ecliptic coincidence. Statistical reasoning says 5% of interstellar objects should arrive within 5 degrees of the ecliptic. We've observed 3 such objects. If they arrive randomly, there's roughly a 14% chance that at least one of 3 would fall in that 5% range. Not unlikely at all. The perihelion during solar conjunction, pure orbital mechanics. The comet's trajectory is determined by its velocity and direction when it entered the solar system, possibly millions of years ago. That trajectory happened to bring it to perihelion at a time when Earth was positioned such that the comet appeared behind the Sun. This alignment affects our ability to observe, but it's not evidence of anything unusual about the comet itself. The large mass selection bias, perhaps. We've only confirmed 3 interstellar objects. The first, Oumuamua, was small and caught only by chance. The second, Borisov, was moderate-sized and discovered by amateur astronomer Gennady Borisov using a relatively modest telescope, Atlas. The survey that found 3I Atlas is designed to detect faint objects. A larger comet with a more prominent coma is easier to detect against the background of stars, especially when crossing the dense fields near the galactic center. There might be many smaller interstellar objects passing through undetected. We're only seeing the ones bright enough and positioned well enough for our current instruments to spot the vigorous plasma activity at perihelion expected. The solar wind was particularly strong in October 2025. The Sun is approaching solar, maximum the peak of its 11-year activity cycle. Enhanced solar wind means stronger interaction with cometary plasma, producing a more prominent induced magnetosphere and brighter ion emissions. Let's consider the broader context. Comets are time capsules, icy bodies that formed 4-6 billion years ago in our solar system, or in this case in another star's protoplanetary disk. They preserve the chemistry of their formation environment. They're made predominantly of ice water, CO2CO, with dust grains of silicates, organics, and some metals. When they approach a star, they warm sublimate and interact with stellar wind according to principles of thermodynamics, fluid dynamics, and plasma physics. We have excellent theoretical models of these processes validated by observations of hundreds of comets and by close-up spacecraft visits to nearly a dozen. We can predict their behavior with considerable accuracy. When you apply these models to 3I Atlas, accounting for its size, composition, trajectory, and the solar environment during its passage, the model outputs match the observations. The brightness curves the spectroscopic signatures. The acceleration magnitude, the plasma emissions all fall within expected ranges. This is the power of the scientific method. We build models based on fundamental physics. We test those models against observations. When they match, we gain confidence that we understand what's happening. When they don't match, we revise the models or question the observations. For 3I Atlas, the models match. The hypothesis that this is a natural interstellar comet behaving according to well-understood physics explains all observations without requiring any unusual assumptions. Take a slow breath and let that sink in. Sometimes the simplest explanation is correct, not because we lack imagination, but because nature often repeats familiar patterns. A comet is a comet is a comet, whether born in our solar system or in another. The physics is universal. That said, science demands we consider alternatives. Even when a hypothesis explains the data, examining other possibilities can reveal new insights or identify observations that would distinguish between scenarios. So let's turn to the second hypothesis. What if something unusual yet still natural is occurring? This is speculation, but it's speculation grounded in physics and motivated by observations. Let's explore scenarios where 3I Atlas might represent something rare yet entirely natural, edge cases of cometary physics that we've never observed before. Scenario 1: Remanent magnetization. Most comets don't have intrinsic magnetic fields. But what if Sky Atlas's nucleus contains materials that do on Earth? Certain minerals, magnetite, hematite, can become permanently magnetized if they form or cool in the presence of a magnetic field. This fossil magnetism can persist for billions of years. Asteroids can carry remanent magnetization. NASA's upcoming Psyche mission will study a metal-rich asteroid that may have a weak magnetic field from its formation in the core of a now disrupted protoplanet. If 3I Atlas formed in a region with strong magnetic fields, perhaps near a young active star with vigorous stellar winds, minerals in its nucleus might have acquired remanent magnetization. Could this affect its behavior? Possibly. A magnetized nucleus wouldn't generate a large-scale magnetosphere like Earth's, but it might interact with the solar wind's magnetic field in subtle ways. Charged particles might be deflected or channeled differently. The induced magnetosphere might be stronger or more stable. The effect would be small. The nucleus is too small, and its possible magnetization too weak to drastically change the physics. But it might contribute to the vigor of the plasma environment and perhaps influence how efficiently solar wind momentum is transferred to the comet, affecting its acceleration. This is speculative. We have no direct measurement of 3I Atlas's magnetic properties. We're too far away for such measurements. But it's a scenario consistent with known physics and worth considering. Scenario 2: Exotic ice structures. We're familiar with water ice on Earth, the ordinary hexagonal crystals that form snowflakes. But water ice has multiple phases depending on temperature and pressure. Ice 2, Ice Phi, Ice 6. More than a dozen crystalline structures exist, and some remain stable at low temperatures, even at low pressures. In the extreme cold of interstellar space, where temperatures hover barely above absolute zero, could exotic ice phases form, perhaps long-range ordered structures, or glassy amorphous ice that transitions to crystalline forms when warmed? If Sky's Atlas contains unusual ice phases, they might sublimate differently than standard water ice, perhaps more vigorously releasing more energy, producing stronger jets. This could explain why the acceleration seems high for the observed outgassing rate. Again, this is speculative. We have limited data on how exotic ices behave under cometary conditions. Laboratory experiments on Earth can create these phases, but studying their sublimation in near-vacuum low-gravity environments is challenging. Scenario 3: Internal structure. Suppose 3I Atlas isn't a solid lump of ice, but rather a loosely bound aggregate, a rubble pile, similar to some asteroids. Such structures form when smaller fragments collide gently and stick together through weak gravitational and cohesive forces. A rubble pile nucleus would have internal voids and channels. Gas produced deep inside could flow through these channels, emerging in unexpected locations. The internal pressure might build until it triggers sudden releases, outbursts that dramatically increase activity for hours or days before subsiding. Comets do show outbursts. Comet 17P Holmes famously brightened by a factor of 1,000,000 in 2007, becoming briefly visible to the naked eye as its nucleus apparently ruptured and released vast amounts of dust. If 3I Atlas experienced such an outburst during solar conjunction when Earth-based telescopes couldn't observe it, might explain the unexpected brightness seen by solar spacecraft. Scenario 4: Radiation processing. During its millions of years journey through interstellar space, 3I Atlas was bombarded by cosmic rays, high-energy particles from distant supernova and other energetic events. This radiation can chemically alter surface materials, creating complex organic compounds, breaking chemical bonds, and changing the thermal properties of ice. Laboratory experiments show that irradiated ice behaves differently than fresh ice. It might sublimate at different temperatures, release different chemical species, or have different mechanical properties. Perhaps this radiation processing created a surface crust that suddenly fractured near perihelion, exposing fresh ice and causing a surge in activity. Take a breath and consider these scenarios. None require new physics. All involve known phenomena: remanent magnetization, exotic ices, rubble pile structures, radiation processing that are less common or less studied than standard cometary behavior. They're the edge cases, the unusual but possible circumstances that might make 3I Atlas's behavior distinctive. Why entertain these ideas if the standard model already explains the observations? Because science progresses by exploring alternatives. Sometimes an unusual observation turns out to be the key to understanding a broader phenomenon. Sometimes it's just noise or coincidence, but you don't know which until you investigate. For example, the unexpected acceleration of Oumuamua into 2017 prompted extensive modeling of how cometary outgassing can produce thrust. Some of that research concluded that even tiny amounts of outgassing too small to produce a visible coma can explain Oumuamua's acceleration. This insight might not have emerged if scientists had been content with initial puzzlement. Similarly, studying 3I Atlas's behavior, even its potentially mundane behavior, advances our understanding of plasma physics, magnetospheric dynamics, and cometary composition. Each interstellar visitor is a data point, a sample of planetary system formation processes elsewhere in the galaxy. With only 3 confirmed examples, every observation matters. That said, these unusual but natural scenarios remain secondary to the primary hypothesis. They're worth investigating, but they lack the strong evidential support that the standard cometary model enjoys. Which brings us to the third category, the bold speculation. This section requires a careful preface. What follows is highly speculative. It represents the what-if thinking that lies at the edge of responsible scientific discourse. These ideas lack strong evidential support. They are mentioned not because they're likely, but because part of science's value lies in clearly articulating even unlikely possibilities, subjecting them to scrutiny, and understanding what observations would be needed to evaluate them. With that disclaimer firmly in place, let's engage thoughtfully with the speculation that has garnered public attention. The artificial object hypothesis was most prominently articulated by Avi Loeb, the Frank B. Baird Jr. Professor of Science at Harvard University and founding director of Harvard's Black Hole Initiative. Loeb has argued in various papers and public statements that humanity should consider the possibility that some interstellar objects might be technological artifacts rather than natural bodies. His reasoning rests on a philosophical foundation. If technological civilizations exist elsewhere in the galaxy, a possibility consistent with the vast number of stars and planets, and if some fraction of them achieves spaceflight, then interstellar space might contain technological debris, probes, discarded equipment, or even functional craft. The probability of any individual object being artificial is low, but it's not zero. And according to Loeb, the consequences of dismissing such a possibility without investigation are high enough to warrant careful examination when unusual objects appear. In the case of 3I Atlas, several characteristics caught Loeb's attention. He co-authored papers and white papers detailing these features, including a document submitted to the United Nations outlining considerations for how humanity might respond if an interstellar object showed signatures of technology. First, the timing. Loeb noted that perihelion occurred during solar conjunction, making Earth-based observation impossible. If one were designing a mission to our solar system perihelion, the point of closest approach to the Sun would be the optimal location for a spacecraft to perform an Oberth maneuver, a propulsion burn that takes advantage of being deep in the Sun's gravity well to maximize the change in velocity. The fact that this occurred when Earth couldn't observe might be coincidental, or it might be advantageous for a hypothetical probe that preferred not to be closely scrutinized during engine operation. Second, the trajectory alignment with the ecliptic. If a probe were sent to survey planetary systems, it would logically approach along the plane where planets orbit, maximizing the likelihood of close passes to multiple worlds. 3I Atlas's trajectory brings it relatively close to Mars, 28 million kilometers in October, Venus 97 million kilometers in November, and Jupiter 54 million kilometers in March 2026, 3 major worlds visited during a single pass. Third, the acceleration. If the observed acceleration were larger than outgassing could easily explain a point still debated, it might suggest propulsion. Not rocket engines in the Hollywood sense, but perhaps careful venting of stored volatiles for trajectory correction or interaction with the solar wind via adjustable magnetic fields. Fourth, the size and mass. A 5-kilometer object is large enough to house complex systems while small enough to accelerate efficiently. It's also large enough to survive millions of years in interstellar space, protecting any internal systems from radiation damage. These points, Loeb argues, don't prove anything, but they make the object worthy of close monitoring for signatures that would distinguish technology from nature radio transmissions, optical signals, anomalous heat, emission deviations from gravitational trajectories, or deployment of sub-objects. Now let's apply critical thinking to this hypothesis. What predictions does it make, and do observations support them? Prediction 1: radio emissions. If 3I Atlas were a functioning probe, it might communicate with its creators, or with sub-probes it deploys. Radio telescopes, including those operated by the SETI Institute and by the Breakthrough Listen project, which Loeb has been associated with, can search for artificial signals. Observation. No confirmed radio signals have been detected from 3I Atlas. Searches have been conducted, but they found nothing distinguishable from background noise or terrestrial interference. This doesn't rule out a probe. It might use directional transmissions, not pointed at Earth, or frequencies we didn't monitor or transmission windows we missed, but it's not supportive evidence. Prediction 2: optical anomalies. A technological surface might reflect sunlight differently than ice and dust. It might be smoother, more specular, or show geometric patterns. Observation. The limited resolution of images even from Hubble 3I Atlas appears, as a diffuse blob doesn't reveal surface details. It looks like a comet irregular fuzzy surrounded by coma. No optical anomalies detected. Prediction 3: thermal excess. Operating systems generate heat. If internal machinery were running, the object might be warmer than solar heating alone explains. Observation. Thermal infrared observations haven't shown excess heat. The temperature appears consistent with solar heating of a dark surface at that distance from the sun. Again, not supportive of the hypothesis. Prediction 4: trajectory changes beyond what outgassing explains. This is where the hypothesis rests most heavily. If the acceleration were definitively larger than natural outgassing could produce, it would demand explanation. Observation. The acceleration is measurable but not definitively anomalous. Experts in cometary dynamics, including the team at NASA's Jet Propulsion Laboratory who specialize in orbit determination, have calculated that the observed acceleration falls within the range explainable by outgassing, especially considering uncertainties in the comet's rotation composition and jet distribution. Prediction 5: sub-object deployment. A mothership might release smaller probes toward planets of interest. Such objects would show up as new, fast-moving objects in the weeks after perihelion. Observation. No such objects have been detected. Surveys like Pan-STARRS and Atlas monitor the sky continuously for new objects. Deploying probes undetected would require them to be small, less than tens of meters, and perhaps not reflective, making them invisible to current telescopes. Possible but unconfirmed. Take a slow breath. What do we conclude? The artificial object hypothesis makes testable predictions. Those predictions haven't been confirmed. This doesn't disprove the hypothesis. Absence of evidence isn't evidence of absence, but it fails to provide positive support. Moreover, the hypothesis suffers from what philosophers call a prior probability problem. We don't know how many technological civilizations exist in the galaxy, how many send probes, or what fraction of interstellar space such probes might fill. Without these numbers, calculating the probability that any given object is artificial is impossible. It might be 1 in a million, 1 in a trillion, or if technological civilizations are rare, effectively zero. In contrast, we know comets exist. We've studied hundreds from our solar system. We've confirmed that objects can be ejected from planetary systems and wander interstellar space. The prior probability that an icy object entering our solar system is a comet is very high. Bayesian reasoning, weighing evidence against prior probabilities, favors the natural explanation overwhelmingly. Yet Loeb's advocacy has value. It reminds us that science must remain open to surprising possibilities. History contains examples of phenomena initially dismissed as unlikely that turned out to be real. Continental drift was ridiculed until plate tectonics explained it. Meteorites were thought to be folklore until chemistry proved their extraterrestrial origin. Black holes were mathematical curiosities until observations confirmed them. The appropriate scientific stance is extraordinary claims require extraordinary evidence. The claim that 3I Atlas is artificial is extraordinary. The evidence so far is insufficient. Therefore, we provisionally reject the hypothesis while remaining open to future observations that might change the assessment, and that's precisely what's happening. The International Asteroid Warning Network initiated a specialized observation campaign for 3I Atlas, coordinating global resources to obtain the best possible data. NASA's Juno spacecraft was recommended to attempt observations during the Jupiter encounter in March 2026. The Galileo project, founded by Loeb and colleagues, continues to monitor for anomalous phenomena. If something genuinely unusual appears, a radio signal, an unexplained maneuver, a thermal signature, it will be investigated rigorously. Until then, the natural hypothesis stands. This is how science should work, entertaining ideas, testing them, and following evidence wherever it leads, without attachment to particular conclusions. Science is not a static collection of facts, but an ongoing process of observation, hypothesis, and revision. As 3I Atlas continues its journey through our solar system, that process continues. The Galileo project, established in July 2021 and led by Avi Loeb, aims to systematically search for evidence of technological artifacts near Earth and in the solar system. The project operates multiple observatories equipped with instruments designed to detect and characterize anomalous aerial phenomena and space objects. In response to 3I Atlas's passage, the Galileo project has been monitoring the sky for any unusual objects that might appear in proximity to the comet, particularly after perihelion, when a hypothetical mothership might deploy subprobes. These observations use wide-field cameras, radio telescopes, and infrared detectors. As of late 2025, no confirmed detections of anomalous objects associated with 3I Atlas have been reported. The International Asteroid Warning Network, IAWN, a collaboration of space agencies and astronomical observatories worldwide, announced a coordinated observation campaign for 3I Atlas. The campaign, running from late November 2025 through January 2026, focuses on obtaining precise astrometric positions to refine the comet's orbit and searching for any deviations from gravitational predictions. IAWN's interest isn't because 3I Atlas poses any danger it doesn't, but because interstellar objects provide unique scientific opportunities. Each one teaches us about conditions in other planetary systems, about how objects can be ejected and travel through the galaxy, and about the interactions between solar wind and materials formed elsewhere. The campaign included a workshop in early November to coordinate observation techniques and data sharing. Participants from dozens of observatories committed to regular monitoring spectroscopy to track compositional changes and photometry to measure brightness variations that might reveal the nucleus's rotation period or surface properties. ESA's Jupiter Icy Moons Explorer JUICE, launched in 2023 and currently en route to Jupiter, had a fortuitous opportunity. In early November 2025, JUICE's trajectory brought it to a position where it could observe 3I Atlas from a unique vantage point. Unlike Earth-based telescopes, JUICE was positioned to observe the comet shortly after perihelion while still relatively active. JUICE isn't a comet science mission. Its instruments are designed to study Jupiter's icy moons, Ganymede, Callisto, and Europa, but its capabilities include cameras, spectrometers, and a magnetometer. Mission scientists planned observations during the window when 3I Atlas was accessible. These observations aim to capture images of the coma structure spectroscopy of gas emissions and potentially magnetic field measurements if the comet's induced magnetosphere was strong enough and JUICE passed close enough to detect it. The challenge: data transmission. JUICE is currently far from Earth, and its communication bandwidth is limited. The spacecraft uses its high-gain antenna as a heat shield while near the Sun, reducing data rates. Scientists expect to receive JUICE's 3I Atlas observations in February 2026, after the spacecraft reaches a position where faster data transmission is possible. These observations could provide crucial context. Viewing the comet from a different angle might reveal jet structures not visible from Earth. Spectra obtained when the comet was still highly active could detect volatile species that have since diminished. Magnetometer readings, if obtained, would offer the first direct measurement of an interstellar comet's induced magnetosphere. Another opportunity arises in March 2026 when 3I Atlas passes within 54 million kilometers of Jupiter. NASA's Juno spacecraft, orbiting Jupiter since 2016, carries instruments capable of detecting radio emissions, energetic particles, and magnetic fields. If Juno's mission team chooses to allocate resources to observe 3I Atlas, and if the comet's induced magnetosphere is still active that far from the Sun, Juno might detect signatures invisible to Earth-based instruments. The value of such observations extends beyond one object. Each interstellar visitor helps refine our statistical understanding of how many such objects exist and what their properties are. 3 confirmed interstellar objects might seem like a small sample, but it's 3 more than we had a decade ago. Extrapolating from these detections, astronomers estimate that perhaps 1 interstellar object passes within Neptune's orbit per year. Most go undetected because they're small, dark, or pass through regions of sky not adequately monitored. Future surveys, especially the Vera C. Rubin Observatory's Legacy Survey of Space and Time (LSST), which will begin operations in 2025, should detect many more. LSST will image the entire southern sky every few nights with unprecedented sensitivity. Simulations suggest it might detect dozens of interstellar objects per year, transforming our understanding from a few anomalies to a statistically robust population study. In that context, 3I Atlas is an early example of what will become routine interstellar visitors studied in real time as they pass through their compositions, measured their trajectories, tracked their interactions with the solar environment observed and compared. This accumulation of data will answer broader questions. What is the chemical diversity of planetary system building blocks across the galaxy? How do different stellar environments produce different kinds of comets? Are interstellar comets systematically different from solar system comets, or are they drawn from the same statistical distribution? It will also prepare us for the possibility, remote but non-zero, that one of these objects might someday show genuinely anomalous properties that demand extraordinary explanations. Until then, the scientific community remains watchful, rigorous, and open to evidence, while grounded in the likelihood that nature, in its infinite creativity, is showing us once again that the universe operates according to beautiful, understandable physical principles. Take a breath and appreciate this moment in scientific history. We're witnessing the emergence of a new field, interstellar object studies. A decade ago, it was speculation. Today, it's observational science. To fully understand 3I Atlas's journey, we must zoom out, expanding our perspective to embrace the vast environment through which it travels. The comet is not moving through emptiness, but through seas of plasma and invisible fields, the cosmic weather that fills the space between stars. Our sun, like all stars, doesn't end at its visible surface. The solar corona, the tenuous, superheated outer atmosphere, extends millions of kilometers into space, and from it streams the solar wind, a continuous outflow of charged particles that fills a vast bubble called the heliosphere. The heliosphere stretches approximately 120 astronomical units from the Sun, 120 times Earth's distance, far beyond Pluto, encompassing the entire realm of planets. At that distance, called the heliopause, the solar wind's pressure balances the pressure of the interstellar medium, and the Sun's influence fades. Voyager A1 crossed the heliopause in 2012 at about 122 AU, becoming the first human-made object to enter interstellar space. Voyager 2 followed in 2018 at 119 AU. Their instruments detected the transition, a sudden increase in cosmic ray intensity particles from outside the solar system, a change in magnetic field direction, and a shift in the plasma environment from solar-dominated to interstellar-dominated. But interstellar space doesn't mean emptiness. The interstellar medium ISM is the gas and dust that fills the space between stars. In our local region of the galaxy, the ISM has a density of roughly 1 atom per cubic centimeter, a better vacuum than anything achievable in laboratories on Earth, yet not true emptiness. This tenuous medium has structure. Some regions are colder and denser molecular clouds where stars form. Others are hotter and thinner, bubbles blown by supernova explosions or stellar winds from hot, massive stars. Our solar system currently moves through a region called the local interstellar cloud, part of a larger structure called the local bubble, which was probably excavated by supernovae roughly 10 million years ago. The ISM also contains magnetic fields, typically a few microgauss in strength, about a millionth the strength of Earth's surface field. These fields might seem negligible, but across the light years of interstellar space, they play crucial roles, guiding the motion of charged particles, cosmic rays, shaping how molecular clouds collapse to form stars, and influencing the large-scale structure of the galaxy. When 3I Atlas wandered through this medium for millions of years, it experienced a very different environment than during its current solar system passage. The temperature was perhaps 6,000 Kelvin hot in terms of molecular motion, but the density so low that the total thermal energy was minimal. The object would have radiated away heat, eventually reaching an equilibrium temperature of just 10-20 Kelvin, barely above absolute zero. At such temperatures, only a few substances remain gaseous. Helium stays gas. Hydrogen forms molecular H2. Everything else freezes solid water, carbon dioxide, methane, ammonia, even nitrogen and carbon monoxide volatiles that would ordinarily evaporate at comfortable Earth temperatures. So the interstellar 3I Atlas was a deeply frozen relic. Its surface, scarred by cosmic ray, impacts its interior, preserving whatever chemical mixture condensed from its birth nebula billions of years ago. It was a time capsule sealed by cold. The object's trajectory through the ISM was shaped by the galaxy's gravitational field. The Milky Way is not a static collection of stars, but a dynamic, rotating system. The Sun orbits the galactic center roughly once every 230 million years, and 3I Atlas's parent star, wherever it might be, has its own orbit. When the comet was ejected from its home system, perhaps by a close encounter with a giant planet or by the gravitational perturbations of a passing star, it embarked on its own independent orbit through the galaxy. Over millions of years, small gravitational tugs from nearby stars, the cumulative pull of the galaxy's spiral arms and encounters with molecular clouds would subtly alter its trajectory. The comet didn't travel in a perfectly straight line. It followed a complex path influenced by invisible gravitational tides. Eventually, by chance, that path intersected our solar system's location. From 3i Atlas's perspective, our sun would have appeared as a brightening star among millions. As distances decreased, solar gravity began to curve the comet's path, not enough to capture it, but enough to bend it into the hyperbolic trajectory that brought it to perihelion. This encounter is temporary. After the March 2026, Jupiter flyby 3i Atlas will recede beyond the orbit of Saturn, then Uranus, then Neptune. By the 2030s, it will cross the heliopause, entering interstellar space again. The solar wind will fade, replaced by the galactic environment. The comet will cool its outgassing, cease its temporary magnetosphere dissipate, and it will wander once more, perhaps for another billion years, until chance or gravity brings it near another star. How many other such wanderers are out there? Current estimates based on the detection rate of interstellar objects and models of planetary system formation suggest there might be 10-15 to 10 or 16 interstellar comet-sized objects in the galaxy, a quadrillion or more drifting in the space between stars. Most will never encounter a star closely enough to activate. They are the galaxy's frozen archive, each one preserving a record of the chemistry and conditions where it formed. Together, they represent the collective memory of billions of years of star and planet formation throughout the Milky Way. Take a slow breath and contemplate that vastness. The space between stars is not a void, but a realm, cold dark, but filled with structure history and the silent passage of ancient travelers. 3i Atlas is one of those travelers briefly illuminated by our sun's fire, revealing a glimpse of the galaxy's frozen memory before returning to darkness. There's a poetic notion grounded in physics that the universe remembers, not with consciousness or intent, but through the preservation of structure in fields, atoms, and light. Every interaction leaves a trace. Every magnetic field encodes history. When we speak of 3i Atlas's magnetic cocoon, we're describing more than a temporary boundary. We're describing information physical patterns that encode the comet's encounter with our sun. Magnetic fields, in a sense, have memory. Certain materials, when exposed to a magnetic field, can become permanently magnetized. This remanent magnetization can persist for billions of years, a fossil record of ancient magnetic environments. Earth's rocks provide a perfect example. When lava cools, iron-bearing minerals align with Earth's magnetic field at that moment. Once solid, this alignment is locked in. By studying the magnetization of rocks of different ages, geologists have reconstructed how Earth's magnetic field has changed over time, including its periodic reversals when north and south magnetic poles swap positions. Mars offers a more dramatic example. The planet once had a global magnetic field generated by a molten core, but roughly 4 billion years ago, the core cooled sufficiently that the dynamo shut off. The magnetic field collapsed, yet patches of Martian crust, magnetized when the field still existed, retain that ancient magnetization. Spacecraft orbiting Mars detect these magnetic anomalies, ghosts of a field that died long ago. Could Atlas carry similar memories if its nucleus contains iron-bearing minerals, and if it formed in an environment with strong magnetic fields, perhaps close to its parent star when that star was young and magnetically active? Then grains within the nucleus might be remanently magnetized. This magnetization wouldn't generate a large-scale field like Earth's. The nucleus is too small and the magnetization too weak. but it might subtly influence how solar wind particles interact with the coma, perhaps stabilizing the induced magnetosphere or affecting where jets form. More broadly, think of magnetic fields as information channels. The solar wind carries the sun's magnetic field outward embedded in plasma. As this field interacts with planets, comets, and spacecraft, it transfers information. The polarity of the sun's field, the timing of coronal mass, ejections, the structure of the sun's corona. Jupiter's magnetosphere, for instance, responds to changes in the solar wind. When a burst of enhanced solar wind arrives, it compresses Jupiter's magnetosphere, triggering auroral brightenings and accelerating particles. By observing Jupiter's response, we can infer properties of the solar wind even if we don't have a spacecraft positioned to measure it directly. Similarly, 3I Atlas's plasma environment encodes information about the solar wind conditions during its perihelion passage. The brightness and spectrum of its ion tail reflect the density, velocity, and magnetic field strength of the solar wind. These observations become data points in understanding solar activity during this phase of the solar cycle. There's a deeper concept here. The universe is fundamentally relational. Nothing exists in isolation. Every object is embedded in fields, bathed in radiation influenced by gravity from distant masses. And these interactions create structure patterns that persist and propagate. Light carries information across cosmic distances. A photon emitted by a star encodes the star's temperature, composition, and motion. That photon travels for years, centuries, or millennia before striking a telescope, delivering its message. By analyzing spectra, astronomers reconstruct events that occurred before human civilization existed. Gravitational waves do something similar. When two black holes merge, they send ripples through space-time. These ripples travel at light speed, stretching and compressing space itself as they pass. When they reach Earth, instruments detect them, and scientists can reconstruct the masses, spins, and orbital parameters of the merging black holes events that occurred millions or billions of years ago in distant galaxies. Even dark matter, which doesn't emit light or interact electromagnetically, leaves traces. Its gravitational influence shapes how galaxies rotate, how galaxy clusters hold together, and how light bends around massive objects. Gravitational lensing. By studying these effects, cosmologists map dark matter's distribution, revealing the universe's invisible scaffolding. 3I Atlas participates in this web of information exchange. Its trajectory through the solar system is shaped by gravity. Its activity driven by sunlight, its plasma interactions governed by electromagnetic forces. Each process leaves signatures in the light it emits, in the particles it releases, in the path it follows. And when it departs, returning to interstellar space, it carries information with it. The thin layer of surface material sublimated away during perihelion passage, but deeper layers remain altered by solar heating. Chemical reactions occurred at the interface between ice and vacuum, catalyzed by ultraviolet radiation. Dust grains that once clung to the surface were liberated, some remaining in orbit around the comet, others drifting away. Years from now, if another star's influence bends 3I Atlas's path, and it passes near a different planetary system, that system's inhabitants, if any, exist, and possess telescopes, might detect it. They might observe its composition and wonder at the elevated nickel content. They might recognize it as an interstellar wanderer and speculate about where it originated. In this way, matter becomes messenger. Comets are the galaxy's postal service, carrying samples from one star system to another, enabling a slow exchange of material across the light years. Biologists have speculated about panspermia, the hypothesis that life, or at least its precursors, organic molecules, amino acids, might be distributed through space via comets and asteroids. While controversial and lacking strong evidence, the basic physics is sound. Organic molecules exist in comets. Comets occasionally cross from one star system to another, and some of those molecules might survive the journey and be delivered to planets where conditions allow life to emerge. Whether or not panspermia occurs, the broader point stands. The galaxy is not a collection of isolated systems, but a connected web. Information flows, matter circulates, and on the longest timescales, the entire galaxy participates in a slow chemical and gravitational conversation. Take a deep breath and consider your own participation in this exchange. The atoms in your body were forged in stars. The oxygen you breathe was produced by stellar nucleosynthesis billions of years ago. The iron in your blood was created in supernova explosions. You are quite literally made of stardust, not metaphorically, but as a statement of atomic lineage. And your existence in turn contributes back. Your body's heat radiates into space. Your breath releases molecules that mix with the atmosphere, eventually escaping to space or being incorporated into future life. Even your thoughts, encoded in neural patterns, represent a local increase in organized information, a brief defiance of entropy. The universe remembers through structure. Stars remember their formation in the chemistry of their atmospheres. Planets remember their impacts in the craters on their surfaces. And we remember through neurons and stories the long history that brought us into being. 3I Atlas remembers its birth nebula in the nickel in its dust. It remembers its interstellar journey in the frost on its surface. And now it carries a memory of our sun written in subtle changes to its chemistry and structure. When it departs, it takes that memory with it, a silent witness to the sun's light in 2025, drifting back into the dark.
Gravity, the weakest of nature's fundamental forces, is also the most far-reaching. While electromagnetic forces shape atoms and molecules, and nuclear forces bind protons and neutrons, gravity's influence extends across cosmic scales, organizing the universe's structure. At the largest scales, gravity weaves the cosmic web, a vast network of filaments, nodes, and voids that spans the observable universe. This structure emerges from the interplay between gravity's attractive pull and the universe's expansion. In the early universe, tiny quantum fluctuations in density regions slightly denser or less dense than average were stretched by cosmic expansion into macroscopic variations. Denser regions had slightly stronger gravity pulling in more matter. This gravitational attraction amplified the density contrasts. The dense became denser, the empty became emptier. Over hundreds of millions of years, this process created a foam-like structure.
Matter collected along filaments where density was highest. Where filaments intersected, galaxy clusters formed massive concentrations of thousands of galaxies bound by gravity. Between the filaments lay voids, vast regions where matter was sparse. Computer simulations of cosmic structure formation starting from initial conditions matching the early universe and evolving forward according to gravitational physics reproduce the observed cosmic web with remarkable fidelity. The agreement between simulation and observation is one of modern cosmology's great successes, a confirmation that we understand, at least in broad terms, how gravity shapes the universe. Our Milky Way galaxy sits on one of these filaments, part of a structure called the Laniakea supercluster, a collection of galaxies stretching across 520 million light-years. The Milky Way and Andromeda, our nearest large galactic neighbor, are both moving toward a region called the Great Attractor, pulled by the gravity of an enormous concentration of mass in that direction. This motion is subtle, hundreds of kilometers per second fast by human standards, but negligible compared to the speed of light. Yet over billions of years, it reshapes the galaxy's position in the cosmic web, illustrating that even the largest structures are not static, but slowly evolving. 3I Atlas, drifting through the galaxy, is subject to these same gravitational influences, though on different scales. Its trajectory is primarily determined by the sun's gravity during its current passage,
But before it entered the solar system, it was shaped by the cumulative gravity of all nearby stars, by the Milky Way's spiral arms, and by the faint tugs of passing molecular clouds. Gravity also plays a role in how comets form.
In a protoplanetary disk, the rotating cloud of gas and dust surrounding a young star gravity causes material to clump. Small clumps grow by accreting more material and by colliding and merging with other clumps. Eventually, these become planetesimals, then planets and comets. The location within the disk determines what forms. Close to the star, temperatures are high, and only materials with high melting points, silicates, metals, can condense. These form rocky planets like Earth and Mars. Farther out beyond the snow line, where temperatures drop below water's freezing point, ice can condense. This is where comets and icy moons form. Giant planets like Jupiter probably formed just beyond the snow line, where abundant ice boosted the amount of solid material available for planet building. Once a planetary core became massive enough, it could gravitationally attract hydrogen and helium gas, becoming a gas giant. The gravitational influence of these giants then determines the comet's fates. Many comets remain in stable orbits in the outer regions, forming structures like our solar system's Kuiper belt and Oort cloud, vast reservoirs of icy bodies. But gravitational perturbations, close encounters with planets, or the tidal influence of passing stars can alter comets' orbits, sending them into the inner solar system or ejecting them entirely. Ejection is how interstellar comets form. A comet in the outer reaches of a planetary system receives a gravitational kick from a giant planet, accelerating it beyond the system's escape velocity. It departs, becoming an interstellar wanderer. This process is probably common. Simulations suggest that planetary systems eject comets continuously, especially during the chaotic early phases of planet formation, when giant planets migrate and scatter smaller bodies. Our solar system likely ejected billions of comets during its first 100 million years. If every star system does this, the galaxy should be filled with interstellar comets, a vast population of frozen wanderers. Current estimates, extrapolated from the few we've detected, support this. Perhaps 10 to 15 or more interstellar comets exist in the Milky Way. Most will never return to any star. They'll drift in the cold dark indefinitely, their closest approach to another star, perhaps hundreds of AU too distant to be gravitationally captured or even significantly warmed. But a tiny fraction by chance pass close enough to a star to experience what 3I Atlas is experiencing now, warming activation interaction with stellar wind, and the brief bloom of a coma before departing again. Gravity also produces one of nature's most beautiful phenomena, gravitational lensing. Einstein's general relativity predicts that mass warps spacetime and light follows the curves in spacetime. When light from a distant galaxy passes near a massive foreground object, another galaxy, a galaxy cluster, or even a black hole, its path bends. If the alignment is nearly perfect, the foreground object acts like a lens, magnifying and distorting the background galaxy's light. Sometimes this creates multiple images or arcs, ghostly reflections surrounding the lensing mass. Gravitational lensing has become a powerful tool. By studying how light bends, astronomers can map the distribution of mass in the lensing object, including dark matter that doesn't emit light. They can also use lensing to magnify distant galaxies that would otherwise be too faint to observe, effectively turning galaxy clusters into natural telescopes. Even individual stars can act as lenses. In a phenomenon called microlensing, a star passing in front of a more distant star temporarily brightens the background star's light as its gravity focuses the light toward us. These events last days to weeks and have been used to detect planets around distant stars and to search for dark matter. Gravity is also how we detect the universe's expansion. In the 1920s, Edwin Hubble observed that distant galaxies appear redshifted, their light stretched to longer wavelengths. The farther away a galaxy is, the more redshifted. This relationship, now called Hubble's law, revealed that the universe is expanding. The expansion isn't galaxies flying through space, but space itself stretching. Imagine dots on a balloon being inflated. The dots move apart, not because they're traveling across the balloon's surface, but because the surface itself is expanding. Similarly, galaxies are mostly stationary in their local regions of space, but the space between them grows, carrying them apart. This expansion has profound implications. It means the universe had a beginning, a time roughly 8 billion years ago, when all matter and energy were compressed in an extremely hot, dense state. That moment, the Big Bang, is when time itself began. Since then, gravity has worked to slow the expansion, pulling galaxies back together. But in the late 1990s, observations of distant supernovae revealed something unexpected. The expansion is accelerating. Some unknown dark energy seems to be pushing space apart, overwhelming gravity's attractive pull. This acceleration means the universe's far future will be very different from its past. Galaxy clusters will remain gravitationally bound, but clusters will drift apart from each other. Eventually, in trillions of years, galaxies outside our local group will recede so far that their light can no longer reach us. The night sky will contain only the stars of the Milky Way and its neighbors. But that's a distant future.
For now, in this epoch, galaxies shine brightly, stars form and die, planets orbit, and comets, like 3i Atlas, drift through the gentle gravitational currents that shape everything. Take a slow breath and feel your connection to these forces. Gravity holds you to Earth, holds Earth in orbit around the Sun, holds the solar system within the Milky Way, and holds the Milky Way within the cosmic web. You are part of this structure, a small eddy in the gravitational flow, a temporary concentration of matter and energy participating in the universe's long, slow dance. Light is the universe's messenger, and learning to read its messages is one of humanity's greatest achievements. Every photon that reaches our telescopes carries information encoded in its wavelength, polarization, and timing. By decoding this information, astronomers can determine the composition, temperature, motion, and magnetic environment of distant objects, including 3i's Atlas.
The technique that makes this possible is spectroscopy, the analysis of how light is absorbed and emitted at specific wavelengths. The principle is beautiful. Every element and molecule has a unique set of wavelengths at which it interacts with light, like a fingerprint. When atoms are heated, they emit light at characteristic wavelengths. Hydrogen emits red, blue, green, and violet lines, the Balmer series, plus additional lines in the ultraviolet and infrared. Sodium emits a bright yellow-orange doublet. Iron has thousands of spectral lines spanning the spectrum. Molecules are more complex. They can vibrate bonds, stretching and bending, and rotate, tumbling in space, and each vibrational and rotational mode corresponds to specific photon energies. Carbon monoxide, for instance, has strong emission lines in the infrared corresponding to its rotational transitions. When light from the sun passes through 3i Atlas's coma gas, molecules absorb some wavelengths, creating dark absorption lines. The molecules also emit light at specific wavelengths as they're excited by solar UV and then relax. By observing which wavelengths appear in emission and absorption, astronomers determine what molecules are present. The James Webb Space Telescope's observations of 3i Atlas in August 2025 exemplify this technique. Webb's near-infrared spectrograph dispersed the comet's light across a spectrum, revealing features corresponding to H2O water, strong vibration rotation bands in the near-infrared CO2 carbon dioxide, distinctive bending and stretching modes, CO carbon monoxide rotational lines indicating significant CO outgassing, carbonyl sulfide OCS, a sulfur-bearing molecule less common but detectable. Water ice grains scattering features from tiny ice crystals in the coma. Each detection tells part of the story.
The presence of CO suggests the nucleus contains volatiles that sublimate far from the sun, explaining why the comet was active even at 4.5 AU when first detected. The water confirms it's a typical icy comet. The carbonyl sulfide hints at sulfur chemistry, perhaps from the breakdown of more complex organic molecules. The ratios of these molecules provide clues about formation conditions. For example, the CO2-H2O ratio varies among solar system comets, possibly reflecting different formation temperatures or processing histories. Comparing the 3I Atlas's ratios to those of solar system comets helps determine whether its chemistry is typical or unusual. Ground-based telescopes contributed complementary observations. The Very Large Telescope in Chile used high-resolution spectroscopy to detect the nickel emission mentioned earlier, analyzing lines in the blue-green part of the spectrum where neutral nickel atoms emit when excited by solar UV.
This nickel detection was particularly interesting. Nickel emission is rare in comets. It's typically seen only in the brightest, most active comets when dust grains are being ablated vaporized near the nucleus. The fact that 3I Atlas showed nickel emission suggests either that it's unusually rich in metallic grains or that its activity was sufficient to release such grains even at moderate brightness. Light also reveals motion. The Doppler effect familiar from the pitch change of a siren passing by applies to light. If a source moves toward you, light waves are compressed, shifting toward shorter wavelengths. Blue. If it moves away, waves stretch toward longer wavelengths. Red. By measuring the Doppler shift of spectral lines from 3I Atlas, astronomers determine its velocity relative to Earth. Combined with positional measurements over time, this yields the comet's full three-dimensional motion, allowing precise orbit determination. The accuracy is remarkable. For 3I Atlas orbital solutions based on observations from May through November 2025 determine the perihelion distance to within a few thousand kilometers, a precision of 0.201%, across a solar system scale. Polarization of light adds another dimension. Light waves oscillate in planes perpendicular to their direction of travel. Natural sunlight has random polarization waves oscillating in all directions equally. But when light scatters off particles, it can become partially polarized, with one orientation dominating. The degree of polarization depends on the size, shape, and composition of scattering particles. By measuring the polarization of sunlight scattered from 3I Atlas's coma, astronomers infer properties of the dust grains. Their size, distribution, are they mostly small grains? Or a mix of sizes, their shape spherical or irregular, and possibly their composition silicates, organics, or ice? Observations showed that 3I Atlas's dust has polarization properties similar to other comets. Slightly negative polarization at small phase angles, viewing angles becoming positive at larger angles. This suggests dust grains typical of cometary composition, fluffy aggregates of submicron silicate and carbonaceous particles. Timing provides yet another layer of information. Some objects vary in brightness due to rotation. If 3I Atlas's nucleus is elongated, and rotating different cross-sections would be illuminated as it tumbles, causing periodic brightness changes. Attempts to detect such variations in 3I Atlas met with mixed results. The coma's light dominates, making it difficult to isolate the nucleus's contribution. Rotation periods of several hours to several days are possible, but without a confirmed detection, the nucleus's spin remains uncertain. This limitation highlights a challenge we're observing 3I Atlas from vast distance, hundreds of millions of kilometers. Even Hubble's sharp vision can't resolve details smaller than a few thousand kilometers at that range. The nucleus itself, perhaps 5 kilometers across, is far below resolution. Everything we see is the coma, and everything we infer about the nucleus is indirect. Yet the inferences are powerful. By combining spectroscopy, photometry, polarization, and models of how comets behave, scientists construct detailed pictures of objects they'll never touch or visit. This is one of science's quiet miracles, learning the composition of a distant object by analyzing the light it reflects or emits. No spacecraft needed, no sample return, required just photons and the knowledge of how to interpret them. Take a breath and consider what this means. The light touching your eyes right now carries information. The color tells you the spectrum. Blue sky means scattered sunlight. Red sunset means light passing through atmospheric layers. Yellow candlelight means thermal emission at moderate temperature.
We are all, in a sense, spectroscopists. We decode light constantly, usually unconsciously. Astronomers simply extend this innate ability using instruments to perceive wavelengths and subtleties our eyes cannot detect. 3I Atlas's light, captured by telescopes and analyzed by spectrographs, has told us that this visitor carries within it elements forged in another star, frozen into ice by the cold of interstellar space, and now sublimating under our sun's gaze. It has taught us something about the chemistry of planet formation elsewhere in the galaxy, and when the comet departs, that knowledge remains a gift of light, a message decoded. We've journeyed together through the story of 3I Atlas, examining observations, exploring hypotheses, and contemplating the broader cosmic context. Now, as this traveler recedes back into the dark, let's gather what we know and acknowledge what remains mystery.
3I Atlas is a genuine interstellar comet, the third such object confirmed to enter our solar system. Its hyperbolic trajectory with eccentricity 6.137 conclusively demonstrates an origin beyond the Sun's gravitational influence. It arrived from interstellar space and will return there. The comet is active. Observations from multiple instruments. Hubble JWST ground-based telescopes detected water vapor, carbon dioxide, carbon monoxide, and other volatiles escaping from a nucleus estimated at 1.4 to 5.6 kilometers in diameter. This places it firmly in the category of icy comets, not rocky asteroids. Its composition is unusual. The detection of nickel vapor in significant quantities suggests a formation environment richer in metals than typical solar system comets, reflecting different chemical conditions in its birth nebula. Non-gravitational acceleration has been measured. The comet's trajectory deviates slightly from what gravity alone would predict, consistent with outgassing producing. Thrust a rocket effect seen in many comets. An ion tail and plasma interactions with solar wind were observed particularly during and after perihelion passage in late October 2025. These observations confirm the formation of an induced magnetosphere and vigorous plasma activity. No technological signatures were detected. Searches for radio signals, optical anomalies, excess thermal emission, or unexplained trajectory changes found nothing inconsistent with a natural comet. The exact composition and internal structure of the nucleus. We know it's icy with elevated metal content, but the proportions of different ices, the presence of organic molecules, and whether the interior is homogeneous or heterogeneous remain unknown. The precise mechanism of acceleration.
While outgassing is the most likely explanation, the specific distribution of jets, the contribution of different volatiles, especially carbon monoxide, and the nucleus's rotation state are poorly constrained. The origin system. We don't know which star's planetary system ejected 3I Atlas, how long ago the ejection occurred, or the trajectory it followed through the galaxy before arriving here. The high velocity suggests a long journey, but specifics are beyond our reach. The statistical significance of its characteristics. Is 3I Atlas representative of interstellar comets or an outlier? With only 3 confirmed examples, we lack the sample size to answer definitively. Observational limitations are inherent. Three-Eye Atlas was faint, never brighter than magnitude. 1112, invisible to the naked eye and challenging even for modest telescopes. The crucial perihelion period occurred during solar conjunction, creating a data gap precisely when the comet was most active. Distance matters. Even at closest approach, the comet remained approximately 270 million kilometers from Earth, farther than the Sun. At such distances, even Hubble can't resolve surface details. Everything we observe is averaged integrated over the entire coma. Complexity is real. Comets are not simple objects. Their behavior depends on composition, structure, rotation, heating history, and interaction with a variable solar environment. Models must balance many uncertain parameters. Uniqueness challenges generalization. Interstellar visitors are rare. We can't yet say interstellar comets typically behave like X because we have only a handful of examples each with unique characteristics. Yet these limitations don't diminish the science. They define it. Science progresses by pushing against the boundaries of what we can measure, infer, and understand.
Every observation of Three-Eye Atlas, every spectrum obtained, every positional measurement adds to humanity's knowledge of comets, plasma physics, and the nature of the galaxy. We examined 3 levels of explanation: the conventional, the unusual but natural, and the speculative. This structure reflects how science should work, prioritizing explanations with the most evidential support while remaining open to alternatives. The conventional hypothesis that Three-Eye Atlas is a natural comet behaving according to established physics explains observations well and requires no new assumptions. This is the working model most scientists accept. The unusual but natural scenarios, exotic ices, remanent magnetization, internal structure effects are worth considering because they push our understanding of cometary science into less explored territory. Even if incorrect for Three-Eye Atlas, investigating them might reveal phenomena relevant to other objects. The speculative hypothesis that the object might be artificial fails to find evidential support and suffers from low prior probability, but entertaining it serves a purpose. It reminds us that science must remain vigilant for genuinely anomalous phenomena, and that we shouldn't dismiss surprising possibilities purely from incredulity. The balance between these approaches is crucial. Too much focus on speculation wastes resources and damages credibility. Too much dismissiveness closes minds to the unexpected. The appropriate stance is evidence-driven openness, follow the data test hypotheses rigorously, and accept results, whatever they show. Three-Eye Atlas continues its outbound journey. By early 2026, it will be beyond Jupiter cooling and quieting. Outgassing will decrease as solar heating fades. The coma will thin. Eventually, beyond Saturn's orbit, the comet will become inactive again, a frozen relic, barely distinguishable from a small asteroid. Observations will continue as long as the comet remains detectable. The Galileo project and IAWN's coordinated campaign will monitor its trajectory through early 2026. ESA's JUICE spacecraft data, expected in February 2026, might provide new insights. NASA's Juno spacecraft has a possible observational opportunity during the March 2026 Jupiter encounter. Each data point refines our understanding, constrains models, and prepares us for the next interstellar visitor. And there will be a next one. Based on current detection rates and the capabilities of upcoming surveys like the Vera C. Rubin Observatory's LSST astronomers expect to detect dozens of interstellar objects per year once that facility reaches full operation. Within a decade, the study of interstellar visitors will transform from anomaly to statistical science. We'll have enough examples to characterize their population size distribution, compositional diversity, orbital characteristics. We'll learn whether Three-Eye Atlas is typical or exceptional. This accumulation of data will answer deeper questions. What fraction of comets are ejected during planetary system formation? How does ejection efficiency depend on the architecture of the planetary system? How common are metal-rich comets? How do different stellar environments produce different comet populations? These questions connect to the grandest question of all. Are we alone? If life's precursors, amino acids, organic molecules, are common in comets, and if comets frequently cross between star systems, then perhaps the ingredients for life are distributed throughout the galaxy. Perhaps life's emergence isn't a singular miracle, but a common consequence of chemistry and time. We don't yet know, but every interstellar visitor brings data, and data over time converges toward answers. As 3i Atlas drifts back into the darkness between stars, carrying with it the memory of our sun's warmth and the faint echo of our telescope's attention, we're left with a renewed sense of connection. This icy wanderer born around another star billions of years ago crossed the vast emptiness of interstellar space and briefly entered our small corner of the galaxy. For a few months, it blazed with borrowed light-shedding gas and dust-painting plasma across space before returning to the silent dark from which it came. It reminds us that the boundaries we perceive between one solar system and another, between here and there, are permeable. Matter circulates, light travels. The galaxy is not a collection of isolated islands, but an interconnected whole with matter and energy flowing between stars on the long, patient timescales of cosmic evolution. We are part of that flow. The atoms in our bodies were once in other stars. The light that warms us was born in the sun's core, 30,000 years ago, slowly working its way outward through dense plasma before bursting free into space and reaching Earth 8 minutes later. When you look up at the night sky, you're seeing light that began its journey years, centuries, or millennia ago. The stars themselves might no longer exist in the configurations you see. You're observing the past. And yet you're also part of the present, part of the universe's ongoing story. Your awareness, your curiosity, your capacity to wonder. These are the cosmos looking back at itself. Take a slow, final breath. Let the weight of this contemplation settle gently. 3i Atlas will not return. Its trajectory carries it away forever back into the realm of the interstellar medium, where it will wander for eons before perhaps encountering another star, another planetary system, other eyes turned upward in curiosity. But its visit mattered. We learned from it. We practiced our science, tested our theories, and expanded our catalog of what exists in the universe. And somewhere in another solar system, around another star, perhaps another observer is watching a different interstellar visitor pass through their skies, asking the same questions we ask, feeling the same wonder we feel. The open question. As 3i Atlas continues its journey back into the deep, carrying with it memories of our sun's warmth and the faint echo of our instrument's gaze, we're left to wonder. In the vast library of the cosmos, what other stories are drifting between the stars, waiting for their moment to pass through our small circle of light? And when they do, when the next interstellar messenger arrives, perhaps one with even stranger characteristics, perhaps one that challenges our understanding in ways we haven't anticipated, will we be ready to listen not just with our instruments, but with the quiet patience required to hear the universe whisper its secrets? The night sky holds countless such messengers. Some will pass unseen, others will catch our attention, and each one, whether ordinary or extraordinary natural, or dare we imagine something more, carries the potential to teach us something profound about our place in this vast, ancient, interconnected cosmos. The silence between stars is not empty. It's filled with possibility. And the story continues. There's a final thought worth holding as we close this chapter of 3i Atlas's story, a meditation on the peculiar relationship between observer and observed, between the human desire to understand and the universe's patient unfolding. When the first humans looked up at the night sky, they saw mystery. The wandering stars' planets moved against the fixed background, their paths inscrutable, Comets appeared without warning, grew bright, then faded, interpreted as omens of change. The cosmos seemed capricious, its rules hidden, but slowly, over millennia, patterns emerged. The Babylonians tracked planetary motions and predicted eclipses. Greek philosophers proposed that celestial objects obeyed natural law, not divine whim. Islamic scholars preserved and expanded this knowledge through centuries when it might have been lost. Then came the revolution, Copernicus placing the sun at the center, Galileo seeing Jupiter's moons through his crude telescope, Newton revealing that the same force pulling apples to Earth also holds the moon in orbit. Suddenly the heavens were comprehensible. Mathematics could describe reality. Observation could test theory. Each generation since has pushed further. We've sent robots to other worlds, placed telescopes in space beyond our atmosphere's blur, and built detectors sensitive enough to feel gravitational waves from colliding black holes billions of light years away. And now we watch interstellar visitors pass through our solar system. We measure their chemistry track. Their trajectories decode the information carried by their light. We understand in exquisite detail the physics of plasma and magnetism, sublimation and radiation pressure. Yet something remains a gap between knowledge and meaning. We can calculate 3I Atlas's orbit to within kilometers, determine its composition to specific molecules, model its plasma environment with sophisticated equations. But the deeper questions linger. What does it mean that the universe allows such wanderers? What does it mean that we arrangements of atoms that were once in stars can now study other arrangements of atoms from other stars? Science provides mechanisms, not meanings. It tells us how gravity works, not why gravity exists. It explains what causes plasma to form around comets, not for what purpose, if any, such beauty exists. Perhaps that gap is where wonder lives. Not in ignorance, we're not wondering what 3I Atlas is. We know it's a comet. We're wondering at the fact that it exists at all, that the universe is so constructed that ice can survive billions of years. Drifting between stars that matter can travel such distances that we can know about it. The philosopher Immanuel Kant wrote about two things that filled him with awe: the starry heavens above and the moral law within. Both point to something that transcends mere mechanism, the starry heavens, not just as fusion reactions and gravitational collapse, but as presence, as the stage on which existence unfolds. The moral law, not just as evolved psychology, but as the capacity for meaning-making, for values that guide action. 3I Atlas, in its passage, becomes part of our story. Not because it's unusual or artificial or even particularly interesting by astronomical standards, it's probably a fairly typical interstellar comet, but because we noticed it, because we chose to study it, because we devoted instruments, time, and attention to understanding this small, frozen world that will never return. That act of attention is in its own way remarkable. We live on a planet facing countless challenges, environmental, social, political. Resources are finite. Time is limited. Yet we allocate some of those resources to building telescopes, training astronomers, and watching comets that pose no threat and offer no immediate practical benefit. Why? Because we're curious. Because understanding is its own reward. Because knowing what exists in the universe expands the circle of what we consider home. When you learn that 3I Atlas carries nickel from another star's supernova, that fact becomes part of your internal model of reality. The universe becomes, in a small way, more familiar. The dark between stars becomes less empty. You're connected through knowledge to processes occurring across incomprehensible scales of space and time. This connection is what science offers, not certainty we're wrong more often than right, and every answer generates new questions. Not control the universe will continue according to its laws, regardless of whether we understand them, but connection, relationship, a sense of belonging to something larger. 3I Atlas doesn't care that we watched it. It has no awareness, no experience. It's ice and dust following trajectories determined by gravity and momentum. Yet our watching matters to us. It makes us more than isolated beings on a small planet. It makes us participants in the cosmos's grand unfolding. There's a reciprocal relationship in observation. The act of watching changes the watcher. When you look at a comet through a telescope, you're not just seeing light reflected off ice. You're connecting your consciousness to an object formed 4 billion years ago, ejected from its home system millions of years ago, now passing through our region of space for the first and only time. Your attention creates a bridge across those scales. In a universe where most events occur unwitnessed, your witness matters not cosmically perhaps, but personally. You become the universe's way of being aware of itself. Carl Sagan famously said, "We are a way for the cosmos to know itself." This isn't mysticism, it's observation. The atoms in your brain, arranged by evolution to process information and generate consciousness, are the same atoms forged in stars. When you think about stars, it's literally stellar matter contemplating its own origins. So what does 3i Atlas teach us beyond the specifics of cometary plasma physics and induced magnetospheres? It teaches us that the universe is vast yet knowable. That distance is no barrier to understanding. That matter connects everything: the iron in your blood and the nickel in a comet's dust share common ancestry in ancient supernova. It teaches us patience. The comet traveled for millions of years before arriving. Science has taken centuries to reach the point where we can study such visitors. Progress is slow, but it accumulates. It teaches us humility. With all our technology and theories, we still can't definitively explain every detail of the comet's behavior. Models are approximations. Understanding is incomplete. Mystery remains, and it teaches us hope. That in a universe of such scale, such age, such seeming indifference to human concerns, curiosity survives. We still look up, we still wonder, we still seek to understand. When 3i Atlas crosses the heliopause in the 2030s, returning to interstellar space, it will carry no memory of us. But we will remember it. The data will remain in archives. The papers will be cited. The observations will inform models used for future visitors. And somewhere, a child might read about this comet from another star and feel a spark of wonder. They might look up at the night sky and realize that space is filled with travelers, that the dark is not empty, that we are part of something unimaginably vast. That spark might lead them to study astronomy, physics, or mathematics. Or it might simply remain as a private sense of connection to the cosmos. Either way, the chain continues: observation leading to wonder, leading to knowledge, leading to more observation. This is humanity's quiet rebellion against entropy to create meaning in a universe governed by impersonal forces. To care about comets, to build telescopes, to study plasma physics, to write poetry about stars, to teach children that the universe, though vast, is knowable. 3i Atlas will be forgotten by most people within a generation. New interstellar visitors will arrive, perhaps more dramatic or unusual. The news cycle will move on, but the fact that we paid attention, that we devoted resources to understanding this small, frozen visitor, that matters. It says something about what we value. Not just survival or comfort, but understanding. Not just the immediate and practical, but the distant and abstract. We are perhaps uniquely among Earth species creatures who look beyond our immediate needs to contemplate the infinite. Take one final slow breath. Feel the weight of your body held to Earth by gravity, the same force that shapes galaxies. Feel the warmth of your skin, energy from the sun, which is the same kind of star that warmed 3i Atlas. Feel the quiet rhythm of your thoughts, electrochemical signals, in neural networks, which are how matter becomes aware of matter. You are connected to everything, not metaphorically, but physically, chemically, atomically. The universe is not something you're in, it's what you are. And consciousness, awareness, wonder, curiosity is the universe's way of appreciating its own existence. 3i Atlas has left our neighborhood, now growing fainter each night as it recedes toward the outer planets.
Soon it will be beyond detection, another anonymous object among trillions drifting in the galaxy's dark spaces. But for a brief moment in cosmic time, it was illuminated. For a few months, it glowed with borrowed light, and we saw it, studied it, wondered about it. That moment has passed, but its echo remains in our data, our understanding, our sense of connection to the cosmos, and that echo, however faint, is enough. The universe continues its slow, patient dance. Stars are born and die. Galaxies merge. Dark energy stretches space. And through it all, on at least one small planet orbiting an ordinary star, conscious beings look outward and ask, "What is that? Why is it there? What can it teach us?" These questions have no final answers, but the asking. The endless, curious asking is what makes us human. So when you look up tonight, if the sky is clear, take a moment to appreciate the darkness between the stars. That darkness isn't empty. It's filled with wanderers like Three-Eye Atlas, ancient and patient, crossing incomprehensible distances. Some are ice and dust fragments of planetary systems long disrupted. Some are rocks scarred by billions of years of cosmic ray impacts. And some we don't yet know might be something else, something that would transform our understanding of what's possible. But whatever they are, they're out there, drifting, waiting, and if we're patient, if we keep watching, they'll pass through our light and we'll learn their stories. The cosmos is speaking. In the language of photons and gravity, plasma and magnetism, it tells us about itself. All we have to do is listen. Sleep well, fellow traveler. The universe is vast, but you belong to it, and it to you. May your dreams be filled with starlight, and may you wake with curiosity renewed.